Hello and welcome. We are studying frequency meter, digital frequency meter, and so it essentially counts the number of rising edges or falling edges of a square or rectangular wave within a pre-specified time. And if the input signal is not square, then we have to convert it into a square or rectangular wave, like a sine wave or triangular wave is required to be converted into a rectangular wave before we can count it. And for that we need a Schmitt trigger, because we could have used comparator, but comparator will not work if the signal is noisy, but Schmitt trigger will work. That's what we have seen. We have seen what a Schmitt trigger does, what is its function, but we haven't discussed the circuitry or how a Schmitt trigger is made. So we will discuss that today using op amps. Okay, so if you recall, once we have mentioned that Schmitt triggers are wrongly connected amplifiers, inverting or non-inverting amplifiers, non-inverting or inverting amplifiers. Okay, so let us see it how it works. So let's start with a non-inverting amplifier. So this is a non-inverting amplifier where a fraction of the output voltage VO, a fraction of the output voltage is fed back to the inverting terminal or minus terminal, and here you give the input, call it Vi. So input is here, and if I call this as say R1 and R2, then this voltage which is fed back is of course VO divided by R1 plus R2. This is nothing but the current which flows in this branch, multiplied by R1 is the voltage across this resistance which goes back here. Now this is non-inverting amplifier. Okay, now let me just tell you a small observation about this circuit. So we know that the op amp increases its output voltage towards the positive supply value if this input, that means Vp, call it Vp, call it Vn, if this voltage is higher than Vn, then op amp will increase its output towards the positive supply value. So this is the positive supply voltage and this is the negative supply voltage. The rule or note, so this is also seen in static characteristic, that op amp will try to increase its output VO towards V supply, positive V supply, if Vp is greater than Vn. So what happens if you give say a positive voltage here, okay, which is higher than say Vn, whatever the value of Vn is at this moment. If you give a voltage here which is higher than the value of current value of Vn, then it will increase its output towards the V supply, and if this is increasing, then of course this voltage will also increase, because this voltage is nothing but VO multiplied by some constant. So that means this Vn will also increase. Therefore, the gap between Vp and Vn will reduce. And if the gap between Vp and Vn is reducing, is going towards 0, then the op amp will not require to increase its output towards supply voltage, V supply. Okay. So, let me just continue this note. Okay. So, if at any moment say Vp is greater than Vn, okay, then VO increases towards the positive supply voltage. So with this symbol, with this shorthand, I mean VO increases, goes up. Okay, and if this goes up, then you see this value is Vn, which is same as a fraction of VO. Okay, so therefore Vn, which is same as a fraction of the output voltage, also increases, right? And thus the gap between Vp and Vn reduces. Okay, so gap between Vp and Vn reduces, and it will happen that op amp will increase its output VO to such an extent so that the gap between Vp and Vn is almost 0. Okay, and it will happen that VO will increase to such an extent that the gap between Vp and Vn will be almost 0, In fact, this is what is called virtual sorting between Vp and Vn. Okay, so this which we called before, which is called virtual sorting. Okay, so the summary of the story is that if ever Vp is higher than Vn, then op amp will increase its output until and unless this point, this potential is almost equal to Vp. Okay, and then at that value of VO, the op amp will stay happily. Okay, because then Vp and Vn are equal, almost equal, and you know that from the static characteristic, from the almost ideal static characteristic, if Vp and Vn is almost close to each other, that means this is Vp minus Vn. If this is close to 0, then output VO will remain can remain anywhere between these two ranges, that is V supply and minus V supply. Okay, so just see that for Vp minus Vn close to 0, Vo lies between plus minus V supply. Okay, so let me rather write minus V supply less than Vo less than V supply. Okay, so this is in this small region. Else, if Vp minus Vn is slightly greater, I mean significantly greater than 0. Okay, so if this is sufficiently greater than 0, that means it's outside the resolution band, then Vo is equal to plus or minus V supply, depending on whichever is higher. Okay, so here what we observe, let me just tell you once again because this is very important, that if ever Vp is higher than Vn, then output will increase until and unless this potential is almost equal to this potential. When these two will be almost equal, then at that value of Vo, op amp will stay happily. Okay, so what we have seen, if Vp is greater than Vn, op amp increases Vo until Vn is almost equal to Vp. Similarly, very similarly, if we see this circuit once again, if ever this potential is lower than Vn, okay, if ever this potential is lower than Vn, so in this same statements we can write with a different color, that if at any moment Vn is less than Vn, then output will decrease. Okay, so I'm writing with a different color, and therefore this value will also decrease, and thus what will happen, once again the gap between this Vp and Vn will also decrease, because if this is lower than Vn, then output will decrease, therefore Vn will also decrease, and thus Vn will come closer to Vp. Okay, so here I write with the red color, if Vn, not Vn, Vp is less than Vn, then op amp decreases Vo until once again Vn and Vp are almost equal. This is how it works. Okay, so this is how the equilibrium establishes. You can try to increase this voltage, op amp will also try to increase this voltage, and thereby make these two equal. Similarly, if you try to decrease this voltage, op amp will also decrease this voltage, and thereby will make Vp and Vn equal. This is how one can understand this non-inverting amplifier. Now, let us see what will happen if we change these plus and minus terminals. So instead of connecting this to plus, I connect it to minus, and here I connect it to plus. Okay, So then I should also call this Vn and this as Vp. Okay. This circuit is no longer non-inverting amplifier. Okay. This is called a Schmitt trigger. Okay. So how will it work? So now you note that what will happen if, say, ever Vn is greater than Vp at any moment. So at any moment, if, say, Vn is greater than Vp, okay, this potential is greater than this potential, then output will decrease towards minus V supply. Then VO decreases towards negative supply voltage. Okay. Now this potential is decreasing. Therefore, what will happen to this potential, which is coming from here? Okay, so this is not N, this is P. This is a fraction of output, potential divider rule. So therefore, Vp, which is same as VO R1 by R1 plus R2, will also decrease because VO is decreasing, right? So if ever this so we started with the assumption Vn is higher. So if ever this value is higher, then Vp will decrease. So if Vn is higher, Vp will decrease. That's what will happen. Then the gap between Vn and Vp will increase further. So gap between Vn and Vp, so this gap will increase. So leading to Vn becoming more and more greater than Vp, because Vp is decreasing. Therefore, Vn will become more and more larger compared to Vp, because Vp is decreasing, right? So this gap increases, and if this gap increases, then output will decrease further. So then VO decreases more, and this way it will continue to happen. Okay. So if I start with that Vn is slightly, so this greater than is slightly greater than Vp, but due to this chain reaction, you can say, loosely speaking, due to this chain reaction, the gap between Vn and Vp will be more and more. Vn will become larger compared to Vp as time progresses, and VO will keep going down towards minus V supply. How long? Until and unless it hits minus V supply. So VO will reach to minus V supply. That means it will saturate. You know, from the static characteristic, output cannot go below minus V supply. So therefore, it will go to only minus V supply. Similarly, if I start with the assumption that Vn is ever slightly less than, okay, so let me write it with a different color. If ever Vn is slightly less than Vp, then VO output will increase, and if the output is increasing, then this will also increase, resulting into that into the fact that the gap between them will increase further. It will continue to increase. So this will remain same. Okay. So here then I should write this will become more and more less than, okay, and okay, and in that case Vयोग will reach to plus V supply, once again saturation. Okay, so when you say read this note, read all the red colored things together, or you read all the blue colored things together. Okay. Okay. So this, in this circuit we observe that output will either go to positive saturation or it will go to negative saturation, positive V supply or negative V supply. So Vयोग can be either plus V supply or minus V supply. That's the only two stable value that the output can take. Okay. Now let us see, so let us continue with this circuit. Okay. So now let us take some concrete example. Okay. So let's take an example. Say R1 is equal to R2, right? Therefore, this Vp will be half of Vo. Right? And say this V supply is equal to, say plus minus 15 volt, plus 15 volt, and minus V supply is equal to minus 15 volt, right? These two are plus minus 15 volt. Now if I write Vi input equal to say 10 volt, what will be the output? So input is 10 volt, output, what will be the value of output? So we know output can be either plus V supply or minus V supply. These are the only two stable values. We have seen this in many different through many different logics. Okay. Now let's see, is it possible that V supply is equal to plus 15 volt? Because it can be only plus 15 or minus 15. Let's see whether this plus 15 is correct answer or not. Okay. So let's check question. So if Vo equal to plus 15, then Vp equal to half of that. Okay. Then if Vo is 15 volt, then Vp is 7.5 volt. Okay. Now this 7.5 volt is here, which is less than Vi, which is 10 volt. So Vn, okay, Vn is equal to Vi is greater than Vp. So output must be negative, output cannot be positive. If Vn is greater than Vp, then output cannot be positive. So the answer is no. This is not possible. Okay. Now, so let's check, can the output be equal to minus 15 volt? Yes, is it possible? Let's check. So, if it is, if VO equal to minus 15 volt, then VP will be minus 7.5 volt, and then Vn, which is 10 volt, okay, Vn is 10 volt, is greater than Vp. Okay, fine. And if Vn is greater than Vp, then Vo should be negative. Okay, so Vo should be negative. Yes, Vo is negative. So this is possible. Answer is yes. So this is possible. So this is the answer. But this is not possible, because in this case, when Vn becomes Vp, this implies output should be positive, but output should be negative, but output is positive. So this is not possible. Okay, so this is the answer. Now let's take another case where input is Vi, or which is same as Vn, is equal to say 5 volt. Okay. Now let's ask, is Vo equal to 15 volt possible? Okay, let's check. Then if Vo is 15 volt, then Vp is 7.5, and in this case Vp is greater than Vn, because Vn is 5 volt. So output should be positive. So it's possible, yes. So output can be plus 15 volt. Okay, so this is possible. This is correct. Now let's check, is it possible that Vo is equal to minus 15 volt? Is it possible? Okay, let's check. If Vo is minus 15, then Vp should be minus 7.5, and then Vp is less than Vn, because this is 5 volt and this is minus, so this is less than. So output should be negative, and yes, the output is negative. So this is also possible. Surprisingly, this is also possible. You see? So both are possible, both are correct answer. So this is possible. This is also possible. So output can take both the values, plus 15 or minus 15, when the input is 5 volt. But the output cannot take two values at the same time. So which value will it take? That will depend on the previous history. Okay. So whether Vo equal to plus 15 or minus 15 will depend on the previous history. Okay. Now I request you pause the video at this moment, or even close it and think about it. What is happening? I mean, there are two answers possible. Just think and convince yourself for a while, and then come back. Okay. So now this is our Schmitt trigger. Let us ask a question. So the question is, suppose at any moment VO is equal to plus V supply. VO can be either plus V supply or minus V supply. So let's assume VO is equal to plus V supply at any moment. And we are changing the input, we can change the input. Okay, so we can change Vi and we want to make VO equal to minus V supply. So the question is, what value of Vi will make VO equal to minus V supply. So this is the question. Okay. So now answer. So first observation is that if I want to make VO negative, when can it be negative? It can be negative only if this value is higher than this value, right? So that means I have to increase Vi. Okay. So let's write VO becomes negative only when Vn, which is same as Vi in this circuit, is greater than Vp. So that means to make VO negative, we have to increase Vn or Vi. We have to increase Vn or Vi. Okay. Now how much? What is the minimum value of Vn or Vi which will surely make, which will make output negative? Okay. So now how much to increase? The answer is as follows. So you just observe that VO equal to plus V supply. Therefore, this point is at a value V supply multiplied by this factor. So Vp, this value I can write Vp is equal to VO R1 by R1 plus R2. Now VO we know is equal to V supply. So here we write V supply, right? So this is Vp, and we have to make Vn higher than Vp. So therefore, Vn should be higher than, or at least slightly higher than, Vp, or which is same as higher than V supply R1 by R1 plus R2, because this is the value of Vp. Okay. So Vn should be greater than V supply R1 by R1 plus R2. Okay. So this is what we have to do. We have to increase Vn, which is same as Vi, higher than this value. If we increase this higher than this value, okay, then the output will become negative. So for example, if I take this equal to plus 15 and R1 equal to R2, then this becomes 15 volt by 2 when V supply is 15 volt and R1 is equal to R2, for example. Okay. So this is the condition, this is the boundary condition where the output will change. I have to increase input by this amount. Okay. Now similarly you can ask the same question, that if at any moment output is negative, how can I make it positive? Okay. So let me ask the completely opposite question. Copy, next page, paste. Okay. So now let me ask the completely opposite question, that suppose at any moment VO is negative, okay, and we can change VI, and what value of VI will make VO positive. Okay, so answer will be again similar. VO becomes positive only when Vn is less than Vp. So to make VO positive, we have to decrease Vn or Vi. Now how much to decrease? So you just observe that once again this is equal to minus V supply. So this is minus V supply. So you have to make Vn should be lower than Vp, and that means lower than this value. Okay, this value. Okay, and if this is minus 15 volt, then this is minus 50. Okay, that's as it is. So now what happens? Let's see. Let's go to the next slide. Okay, and so let's see how the input and output changes. Okay, so if output is negative, then Vi less than this. If Vi is decreased, then if Vi is decreased below this minus V supply by R1 plus R2 multiplied by R1, am I right? Yes. If it is decreased below this, then VO becomes plus V supply. Similarly, if VO is plus V supply and if Vi is increased above plus V supply R1 by R1 plus R2, then VO becomes negative. Okay. So suppose let me draw some timing diagram like this. This is time versus VO, and this is time versus Vi. Okay. Now Vi, let's assume that VO is initially plus V supply. This is plus V supply, and this point is minus V supply. Okay, and let's call this point on the Vi line is equal to this. Okay, so this, let me just give it a name. Okay, because I cannot write this big expression in this small space. So let me give it a name. Let me just give it a name, LTP call it LTP, and this you call as UTP, lower trigger point and upper trigger point. Okay. So here I write this UTP and here I write LTP. The value of LTP is same as this and value of UTP is same as this. Now you see that if the output is positive and if you increase Vi above UTP, okay, say if you increase Vi from some initial value, we don't know what is the initial value, so maybe here, if you increase it and cross this point, then the output will become negative. So at this point output will become negative, and then it will stay negative as long as you keep the input here, or actually as long as you keep it above LTP. Okay. But if you bring the input below this value, that means this value, like this, here at this point output will become positive again. So this is how it works. This is exactly like a Schmitt trigger, right? This is the upper trigger point of a Schmitt trigger, lower trigger point of a Schmitt trigger. The only observation is that it's a inverted Schmitt trigger. You can call, because when you see input increases, output decreases, and here input decreases, output increases. So this is a inverted or inverting type Schmitt trigger, since output decreases when input increases. Okay. So this is called a inverting type Schmitt trigger. And one small fact, we have started this by changing the plus minus sign of a non-inverting amplifier. So if you start with a non-inverting amplifier and change the plus minus sign, it becomes a inverting amplifier, inverting Schmitt trigger. So start from non-inverting amplifier and change the plus minus sign, it will become inverting amplifier. Just you can note this point. Okay. And this is otherwise just like a Schmitt trigger. Only thing is that it's opposite, but there is still a upper trigger point, there is still a lower trigger point, and this is the hysteresis band. Hysteresis band or hysteresis gap. So this is like a Schmitt trigger, but it's inverted. Okay. So now let us quickly see another type of Schmitt trigger, which is non-inverting type. Okay. So now non-inverting Schmitt trigger. Okay. And to make the circuit, what we have to do? We have to start from a inverting amplifier and change the plus minus sign. Okay. So we will start, say, from a inverting amplifier, minus plus, give a negative feedback, this is R2, R1, I ground it, this is the input, this is what? This is inverting amplifier. Okay. Before proceeding, I request you that you do a stability and equilibrium analysis of this circuit on your own. I'll just tell you very quickly that if ever say this this is Vn, this is Vp, if ever say you increase Vi, which will cause Vn to increase, okay. So if ever, I'll just give some symbols. If Vi is increased, then of course Vn will also increase, because Vn is some sort of average of this Vi and Vo. So if you increase Vi, then output then Vn also increases, and if Vn increases, this is at 0. If Vn is trying to increase, output will try to decrease, right? Because negative input is increasing, so output will decrease. Now if output is decreasing, this will cause Vn to go down, right? So you are increasing Vi and op amp is decreasing Vo, and therefore you are trying to increase Vn, op amp is trying to decrease Vn. So op amp will increase its output until and unless Vn is again brought back to the same value as Vp, which is 0 volt. Okay, so I'm not writing these details things which I did for the previous one due to lack of time. You do it yourself. If you need any help, I'll be happy to assist you, no problem. Okay, so do the stability analysis. Yourselves. Homework. Okay, so now let us start with this inverting amplifier, and let's switch this plus minus signs. Okay, so I will make this plus with a different color to highlight it, and this minus. Okay, so now I should also call this as Vn and this as Vp, right? So this will become a Schmitt trigger. Okay, now I request you that you do the stability analysis or equilibrium analysis of this circuit on your own, because you already have done that for the previous circuit. So I will not write it in detail, but I will just briefly mention. Say if at any moment, if say Vp is, let me first erase it. Say if at any moment Vp is higher than Vn, then what will happen? Then the output will increase. If Vp is higher, then output will increase, which will cause the Vp to increase further, because Vp depends on Vo, like this. Vp is always an average of Vi and Vo. VIR2 plus VOR1 by R1 plus R2. Okay, so if I have Vp higher, output will increase. Okay, if output increases here, then Vp increases further, and if Vp increases, output will increase even further, and then due to this chain reaction, okay, loosely speaking, informally speaking, due to this chain reaction, output will keep increasing and will go to positive supply voltage, okay, plus V supply. Similarly, if Vp is lower than Vn at any moment, then output will decrease, which will cause Vp to decrease further, and with this chain reaction, output will go to minus V supply. Okay, so homework, you just convince yourself thoroughly that due to chain reaction, Vo goes to plus V supply or minus V supply, and these are the only two stable values. That the output can take, that VO can take. Okay, and okay, so output can take only these two values. Now I will request you to play another small game. The game is like this. So you take, say, different values of input. Okay, make a table like this. Vi, you choose the value of Vi as 0 volt, 5 volt, minus 5 volt, 10 volt, minus 10 volt, etc. And ask, is VO equal to plus 15 volt possible? Yes or no? Ask this question. Okay, for all these different values. Similarly, ask, is VO equal to minus 15 volt possible? See, is it possible or not? And we will see that for some input only one output is possible, and for other input both outputs are possible. Okay, just see it. It is a nice fun. It's a nice game. You just play with this. Okay, like we did for the previous circuit. This time you do it yourself. Okay. Now let us ask a question that suppose. So the question is, suppose VO is negative at some moment, okay, and we can change Vi. So the question is, how can we make output positive by changing input? Okay, how can we make VO equal to plus V supply by changing Vi? So this is the question. Okay, so let's see what's the answer. So first question is, do we have to increase Vi or decrease Vi? The answer is we have. So we want to make output positive. When can the output be positive? Only if Vp is higher than Vn. So we have to increase Vp. Okay, and we can increase Vp by increasing Vi. Okay, so to make VO greater than 0, we need Vp greater than Vn. Okay, so we have to increase Vp, right? And how can we increase Vp? By increasing Vi, because Vp is nothing but Vi multiplied by R2 plus Vo multiplied by R1 by R1 plus R2. Okay, so we have to increase Vi, because if Vi increases, then Vp increases. But how much? Okay, at least as much, so that Vp becomes higher than Vn, and Vn is equal to 0. So at least Vp should be greater than, slightly greater than Vn, which is same as 0. Okay, now Vp is this, so let's write Vi R2 plus Vo R1 divided by R1 plus R2. This should be greater than equal to 0, and okay, and from this this goes away. So from this we can write VIR2 plus VOR1 greater than 0, from which we write VI should be greater than minus VOR1 by R2. Now in place of VO, we can write the current value of VO, which is same as minus V supply. This is the current value. So it becomes minus minus plus V supply R1 by R2. Okay. So this is the condition. Vi should be greater than this. This is the boundary value. If I increase Vi above V supply R1 by R2, then output will go to positive value. Okay. So this is the condition. So you can take an example like this is equal to 15 volt and say R2 equal to twice of R1, then you have to increase Vi above 7.5 volt. Okay. So like Vi should be greater than 7.5 if if R2 is equal to 2 R1 and V supply equal to 15 volt. Okay. So this is an example you can take. Okay. Similarly, you can ask the same question that if VO is negative, if VO is positive, then what should we do to make it negative? Okay. So copy, next page, paste. So if this is positive, how can we make it negative? So you see that to make it negative, we have to bring this value down lower than 0, and that is possible by bringing Vi down sufficiently. So answer, we have to decrease decrease Vi. Now how much? At least we have to make Vp equal to less than 0 volt. Okay. So we have to make it Vp to make Vp less than 0 volt, which implies Vp is nothing but once again R2 Vi plus R1 VO by R1 plus R2 less than 0. From this you can write Vi less than VO R1 minus VO R1 by R2, which is same as, let's put the current value of VO. So we have to bring it down, V supply R1 by R2. Okay. So this is the boundary condition, Vi less than V supply R1 by R2. If you bring it below minus, there is a minus, this minus. Okay. If you bring it down below this, then the output will change. Okay. So very quickly, so this value I will call as lower trigger point. LTP is equal to minus V supply R1 by R2, and this value I will call upper trigger point. Okay. So now you can do a timing analysis, take time versus Vi and time versus output. Output can be either V supply or minus V supply, and Vi on Vi axis mark these two values, LTP which is this, and UTP, which is the negative of this. So this is the UTP. So mark these 2 points. You start with the assumption, say output is initially positive here, and then input is changing. Okay, so the input is changing. When will the output become negative? For the output to be negative, you have to bring the input below lower trigger point. So say here it goes down below lower trigger point, then the output at this point will go to minus V supply. And then say input is again changing. When will it make the output positive? The moment when the input goes above upper trigger point. So say here. So here output will become positive. Okay. So this is how it works, and you just say this is just like a normal Schmitt trigger. When input decreases, output decreases. If input increases, output increases. So this is not a inverting Schmitt trigger. This is a normal Schmitt trigger, non-inverting Schmitt trigger. So this is a non-inverting Schmitt trigger. Since you observe that output increases when input increases, and vice versa. If input decreases, output also decreases. So this is a non-inverting Schmitt trigger. Although we have just started this from an inverting amplifier. So if you start with an inverting amplifier and switch the plus minus sign, it will become a non-inverting Schmitt trigger. Okay, thank you.